Okay, so we're going to write some parallel stuff. So we look at various different techniques for powers. We talk about rival powers and different types of powers, and which hopefully going to spend the majority of the time inside Visual Studio. And I'm not mic'd up, and that's going to annoy the person at the back who's recording this. Do you want me to put the mic on?
Yes, please.
You're a bit slow on your hands today.
I know.
You're at the pub.
Unfortunately not yet.
You sure? Okay, is that one?
Should be.
Sounds like it.
Yeah. Thank you.
Okay, is that okay? Okay. So we're going to talk about patterns and parallel patterns. I'm trying to spend most of my time in Visual Studio. I don't think you really want to look at time in terms of slides. So we've got a reasonable amount of stuff to get through. Hopefully we can get through it quickly because Rich isn't studying. And that's recorded, it's going to be really upset. So the free lunch is over. You guys know this is a myth, right? Because since Monday you've been having free lunches, right? Yes? Have there been good free lunches? Yeah, you've been pleased? Okay. So the free lunch is over. There's a guy called Love Sutton at Microsoft. And he wasn't talking about the canteen at Microsoft. He was actually saying that effectively before about March 2005, if you want your code to go faster, yeah, effectively you had two choices. You can either spend time re-engineering your code, yeah, to get some extra bits of performance out, or alternatively you just throw more cores out. Sorry, throw more cores out? No, not throw more cores out. You can basically go and buy a new CPU from Intel, and hey presto, your application got faster. So the free lunch was the fact you didn't have to spend engineering dollars. But after March 2005, things started to get a bit of a problem. The fact that Intel said, we can't increase the clock speeds at the same kind of rate that we did previously. So if you want your code to go faster, that's going to be a bit of a problem, right? In fact, that the only way they can do it is to give you more cores. Single-threaded application doesn't go any faster, yeah, if you throw more cores out. In order to go faster, you've got to spend engineering dollars basically targeting multiple cores. Okay, so the free lunch is over. To make things go faster as we add more and more cores, you're going to have to re-architect your code to take advantage of those cores. What we'd like to do ultimately is get back to the free lunch. And I'll ask you at the end, as we talk about various patterns and various techniques, whether there's a technology there today that actually gives you that same kind of free lunch. But that's what we're going for. How many CPUs do most of you target at the moment? How many people target applications that have 4 cores? 8? 16? 32? 64? So they reckon in about 5 years' time, we should certainly be starting looking at, 16, 32, even bigger than that. And years ago, Intel predicted 256 by about next year. But they've had problems with fabrication and various other things. But if you look at GPUs, for example, how many processors on a GPU? Loads, that's a good number, isn't it? Very accurate, that. There's loads. Did you do good maths at school? So, it's about, GPUs, 512,024, but these aren't general processing units. They're very much lockstep kind of things for doing vector processing kind of stuff. But there definitely is a possibility out there that we could be talking 64, 128 cores, certainly in our life. So, one of the needs for parallelism isn't the fact that there is algorithms that we previously couldn't solve on a single core. It's all about basically producing better results in the same or smaller period of time. So if you take gaming, who's got an Xbox One? No one! That's bullshit. PlayStation 4? Oh, come on, this is a room full of geeks. One person. I just don't believe that. There's my tool, right? So the big thing, on your PlayStation 4, you feel privileged? You're the only one in this entire room that has that as a kid. You must feel privileged, right? The graphics on it, are they good? Okay, this analogy's not going to go very far, is it? So, on my son's Xbox One, because I love him and I have bought an Xbox One, the graphics are pretty amazing, right? But they're not photorealistic. Can we produce photorealistic graphics today? Not in real time, but if you go to the cinema and look at the CGI that's being produced by things like gravity and that kind of stuff, it's pretty damn awesome, right? But obviously it's not doing it in real time. So that's where we want to get to. We want to do it in a gaming environment. So over time, as we add more and more cores to a gaming engine, we can get closer and closer to that kind of stuff. Artificial intelligence inside games. Again, your ability to interact with non-human-like players. Again, we need a certain amount of compute to give you better and better responses in a realistic time frame that makes the game playable and that kind of stuff. So the thing that often driving parallelism really is all about processing more and more data in the same period of time, to give you kind of real-time kind of results. So there's a famous guy called Randall who basically said, whoa, before you start getting carried away about throwing multiple cores in your application, you need to understand your application. You need to decide whether you can parallelize it. Is it possible? There's a set of numbers called Fibonacci numbers. What are Fibonacci numbers? Don't say lots of them. What are Fibonacci numbers? Some of the previous two numbers. They are 1, 1, 2, 3. Oh, I thought we got a smart bunch today. 5, 8, 13. Okay, let's leave it there. So it's the sum of the previous two numbers. Can I parallelize the computation of Fibonacci numbers using that algorithm? No, because the sum of this number is equal to the sum of the previous two numbers. The algorithm is inherently sequential, so you can't parallelize that. In fact, if you look at lots of applications, there will be some element of what you're doing that can be parallelized and some can't be. Okay, so some bits will be inherently sequential, some won't. Let's take and make it a cup of tea. Do you want to know how to make a cup of tea? It's a British thing, really. What do? Well, we perhaps take the cups out of the cupboard, we put them down, we get the teapot, we wash the teapot out, we put it on the side, get it ready, fill up the kettle, put it on to boil. Once it's boiled, we pour that on top of the tea leaves that I forgot to mention, we put the teapot and we pour on. We leave it to brew, and then once it's brewed, we pour into the cup. Okay. Now, my mother-in-law is a teaholic. She really likes to make cups of tea real quick. That takes a certain period of time. Can we speed up that process? Can we run it in parallel? Some of it, okay? Clearly we can't pour the tea before it's brewed, right? Otherwise it's moan and it doesn't taste good, right? So what we have to do effectively is instead of getting the cups out first, what do we do first? Fill the kettle. That's the thing that takes a long period of time, so we boil the kettle up. And then while the kettle's boiling, we fetch the cups, we wash the teapot out, we put the tea in it, and hopefully things are perfect. The moment that kettle finishes boiling, we're just about ready. We pour it on, we leave it to brew, and then we make a cup of tea. Can we do it even faster than that? What do you reckon? Yeah?
2 kettles.
2 kettles! Wow! You live in a very luxury household. We have 2 kettles. So we could use 2 kettles, right? We could take 2 kettles, fill them both with half an amount of water as originally, put them on to boil, and they should boil mathematically twice as quick as the previous one. Could we go even faster than that? 3 kettles! Okay. Excellent. Okay, we could do that. 4 kettles, 5 kettles. We could do an infinite number of kettles boiling an infinitely small amount of water would boil in an instant. Yeah. Is this a good plan? No? Why not? Shall we remake? Yeah. This is a I don't know what to call it, a theoretical example because we don't have infinite kettles. The problem with that is we spend a lot of our time doing what? Making kettles. I've got quite a few demos to do today. I'm guessing that's not going to happen. So we basically spend a lot of our time doing overhead. Parallelism isn't free, right? The moment you say you want to run stuff in parallel, you have to introduce extra code in order to orchestrate that process of fetching things, putting them in the right place, getting work scheduled and running. So breaking things into really tiny, small pieces kind of makes sense. But if you think about it, to make those tiny pieces work, you need some extra code in order to orchestrate that little piece of work. Okay? So think about a couple of things. One, can you parallelize the whole algorithm? Possibly not. You can only parallelize bits that are not inherently sequential. But even if you find bits you can parallelize, you've got to be careful that you don't break it down into too finer chunks, because there's going to be extra overhead required in order to achieve that. So Amdahl's law is basically saying, if you can only parallelize 10% of the algorithm, you're only getting a maximum of 10% speed up. That 10% going to nothing, theoretically. The other thing to bear in mind, obviously, if you take an algorithm, run it on 1 core, and it gives you this time, and you run it on 4 cores, and it takes a quarter of the time, what do you know? It's just not true, is it? Right? There's no way on the planet that's ever going to happen. Right? Okay? So, effectively, things can't scale quite as easily. Types of parallelism, we have coarse grain. Coarse grain is what most people are used to. It's something we've been able to do for years. A web server is an example of coarse grain parallelism, because a server handles multiple requests at any one time on the web server. Each request is independent of each other. Okay? Other types of coarse-grained parallelism, payroll processing. Hopefully my paycheck is different to someone else's paycheck calculation. It's not dependent on each other. We can obviously run those independent of each other too. The place we're going to focus on today, though, is this thing called fine-grained parallelism. You see, coarse-grained is easy on the server. We have lots of requests coming in. Each request is handled independently. There's work being generated by lots of requests. Fine-grained parallelism is more around about things like desktops. If we can end up with 16 calls on your desktop, what are you going to use them for? You fire up Word? What's Word going to do? If I take one call from the UI, what else could it be doing? Spell check in the background? What else? Grammar check? Printing, maybe? Autosave? We're struggling now to come up with uses for those calls, right? So, what would you do with all those other ones? The other alternative, you could fire up Outlook, couldn't you? But what would Outlook do? It'll take every one of those calls by one. So, the only way the Word guys can make use of your 16 calls is to do fine-grained parallelism. Not coarse-grained having a call per task, like grammar checking or spell checking. They can take the grammar checking or the spell checking and they can break it down into smaller granularities. You might spell check multiple paragraphs in parallel. Okay? So we use multiple calls acting on different things. This is what we call fine-grained parallelism, and potentially this is where things get a little bit more tricky. So, what I'm hopefully going to talk to you about in the next hour and 15 minutes is a whole series of different patterns for doing parallel programming. Okay? So in the same way we have design patterns for object orientation, we have patterns for parallelism too. Some of the most common ones I put up here, fork and join, we'll talk about effectively base, kick something off onto multiple threads, when we've got all the results in, bring them back together again. Pipeline, if you did TPL data flow yesterday, I'll show you an example of data flow where we have like a production line, we'll put some data in at one end, and hopefully each of the stages are acting in parallel. Geometric decomposition, we've got a huge amount of data. It's like an array of values, and we want to break it down into chunks, and we can give out different parts, different threads in order to hopefully work on it in parallel. That's the plan. Loops, big place for parallelism. Loops are all about doing lots and lots of things. Yeah? And so effectively, if we can effectively take a loop and say, this call does this part of the range, this call does this part of the range at the same time, life is good. We can only do that if we don't care about order. And there's no dependency between these things. So not everything can be parallel just because it's a loop. Functional programming, this is often seen as the holy grail for parallelism. All the data is immutable, we're just passing things around, takes input, produces output. F#, anybody here program F#? Yeah, a few here, yeah. Good for parallelism? That's why we're using it. It's a painful language, there has to be some benefit. And then finally, we have this thing called Monte Carlo. Who's using Monte Carlo? No one. Some of you work, I guess you can't admit you work in a bank these days, can you? Business. So the bank use Monte Carlo as a way of saying, well, we don't have enough time to give you the proper answer, so we'll make a guess. Okay? So if you've ever invested in a bank nowadays, it's not a big surprise, is it, right? I mean, we'll just take a guess, because it's better than nothing. So these are the kind of patterns that we're going to talk about today. Okay. So very simply, fork and join. So I'm going to use Microsoft's Parallel Framework extensions as a mechanism to use patterns. Parallel Framework extensions came out in .4. There's a class on there called Parallel, got a very simple one, Parallel.invoke. You give it methods, and it'll basically run all those methods in parallel. When all those methods are completed, you then start executing the next line of code after it. This is classic fork and join. Okay? Similarly here, we've got another example of fork and join. Here we're kicking off 3 tasks. Yeah? So we've got tasks of in, some X, some Y, some Z. All these 3 operations run independently. I can therefore kick them off in parallel, and when they're all done, combine the results. This isn't that dissimilar from how we write the sequentially. We might call methods some X, some Y, some Z, and add them together. All we're doing now is just wrapping them up in a task. So it's a relatively simple fork and join style pattern at this point. Okay. Perhaps a more complicated fork and join style pattern is divide and conquer. Divide and conquer, I have some data that I need to process, well, I'll break it in half. You do that half, you do that. And then this one said, well, that's still too much for me. I'll subdivide it again. Okay, I'll delegate again and again and again and again. So you keep dividing the work up into smaller and smaller chunks, and then at the end you have to merge all the results back together. Okay? One of the classic places where we can use this is quicksort. Okay? All familiar with quicksort? Yeah, all nodding. Yeah. Okay, so let's do divide by, I guess. Okay. So, can you all see this in the back? Is that a yes?
Yes.
Yes. Okay. Well, you hear me in the back, I guess I should have asked for that. Okay, so you can't see. Can you see that now? Yes, all good. Is that good? Okay, good one. I'm asking to show you. Right? So we're going to create an array of random numbers, and then I'm going to exercise a sorter, which is basically a timer. And there's the quicksort algorithm. Miss Sharper's not a name. So quicksort is going to run here. Okay, quicksort is what type of algorithm? It's recursive. Okay, so if you look here, we come into quicksort, and we're basically we pick a random position in the list of numbers as a pivot point. Yeah, all numbers below the pivot point are going to get sent to one version of the quicksort method. Anything above that number are going to get sent to another one. And since it calls itself back again, it's going to keep doing that until it gets down to just a couple of numbers in each bit. Okay, and then it combines them all back together again. Yeah, so that's the standard quicksort. What we're going to do is we're going to write a parallel version of this. Okay, hopefully it's not going to be too hard. So, let's go and rob it. So let's go. Oops, too much. Okay. And we're going to rename it to parallel quicksort. Okay. So what are we going to do here now? So instead of calling quicksort at the moment, this runs on the main thread. Once that's finished, we then do that on the main thread, and then when that one's done, we do that on the main thread. Okay, so instead of doing that this time, we're just going to change these blocks of code. Take this like this. First result equals task.factory, that's start new. That's going to produce me a list of. Okay. Sorry? Well, I missed one out. Yeah, thank you. Okay, and what I'm going to do now is I'm going to not call quicksort here, I'm going to call okay? Okay, as far here, second result equals task.factory, that's new again. Okay. And finally, so we're not drastically changing the structure of the algorithm here, right? And that's kind of important. If we want parallelism to catch on, we don't want to radically change the structure of the algorithm. Right? We want to make it easy to read as sequential code, yeah? But obviously running in parallel. Okay, all good? Okay, and then hopefully I can say here that for our result equals what? First result. Dot result. Dot concat with the second result. Dot concat. Oh, thank you. And third result. Alright. Interesting comparison. Oh, it's two listed. Okay, so we've got a parallel version. Okay, so we're going to execute both so we can compare them. Okay, which one's going to go faster, you reckon? Hopefully the parallel one. Here we go. Okay, let's go. We're in release build. Okay, so we're sorting. Parallel one took 4.0 seconds, and the so we'll tell you 1, 2. That was worth the effort. I mean, if you run it again, let's just run it. Okay, so we can see that we are actually starting to use quite a few cores. Yeah, so we're not yeah, and then effectively the next one runs that one. So the problem is that we've got the situation with the kettles here, right? Okay? Effectively, we keep subdividing. And every time we subdivide, we create free tasks. That's not free. That's work above and beyond what we did on the single thread. It's not free. It's going to cost us stuff in order to orchestrate and do that kind of stuff. So yes, we can do divide and conquer, but at some point we have to decide, you know what, we've gone deep enough. We've kicked off enough tasks, we need to revert back to just keep something running on the same thread that these tasks are running in parallel. So there's a depth parameter that's been passed around, which obviously we don't need for the regular one, but I need it for this one. So inside the parallel version, that's the parallel one. So we basically pass in each time a current depth plus 1. Okay? So what I'm going to do here is I'm going to define a function of list t, and that's going to take int. It's going to turn list t. And that's going to be my sort method. Okay? And my sort method by default is going to be my parallel. Okay? But if the depth is greater than 4, I'm going to say the sort method equals. Okay? So I'm basically making a switch inside the code. If we've gone down 4 levels deep, I'm going to revert back to regular quick sort. Okay? So instead of calling parallel quick sort here, I'm just going to say sort method. Summary here. Okay? Go run the code. It's sorting away. That took 1.4 seconds, and the regular one took 2.15. Okay, so it was a decision. We got some benefit from parallelism, but because we kept doing the same finer and finer grain, and I've only got like 4 real cores, there's a point where you're just paying lots of costs of overhead. Right? So we need to balance farming stuff out with the resource that we have available to us. If I had 256 cores, I probably could have gone down way deeper than that in terms of depth. Okay, but obviously I've only got 4 cores. They can only ever be processing one thing at any one time. There's each of those different cores. Okay, any questions with that? All good? Yeah? Okay.
Is there any way that you just get the program to decide that level itself? Do parallel if
you'd be out of a job then, wouldn't you? So can you do that? The thing about this is, right, lots of people say, oh yeah, we can put stuff in the framework. It has to try and work these things out sometimes. So a lot of stuff we're going to talk about when we talk about peeling and TPL data flow and parallel 4, it tries to work it out, but it's not psychic. I mean, it can only work it out as it starts running your code and realizing the pieces of work it gives you, that you give it, are too small, which case it might grow no matter work with a task. To do parallelism properly, you have to understand the machine. Right, so code that runs quicker on one architecture, 4 cores, 8 cores, this amount of memory, won't necessarily be performant on something that has very different number of processors and different cores. Amount of cache you have on the CPU. Yeah. So if you care about parallelism, you have to, and you want to get the best bang for buck, you have to understand the hardware you're running. If you don't, who knows? Okay, so another type of parallelism that we've got is geometric decomposition. This is kind of a standard one. So when I left university, I worked for a supercomputer manufacturer, and that's what we did. We parallelized algorithms for people like the weather people, so we could try and predict the weather. Yeah? Apparently, the best algorithm for predicting the weather is a 50% chance the weather tomorrow is the same as today. That's not bad odds, right? So, but we used to do things like predicting the weather. So, you know, we have to run simulations. So all over the world, we've got sensors on this map. And then we run algorithms against chunks of the world, right? And you could say, well, if this is the whole world, this machine will just process this bit, and this one will just process this bit, and this bit, and this bit. So you can divide it up into little chunks. Can they run independently of each other? Unfortunately, the weather doesn't just end on a boundary. That would be kind of cool. Okay? Weather ends here. We can't do that. So what's happening is they're going to have to like stay in lockstep with each other. They're going to do an iteration of a period of time based on the current sensors in their region and the overlaps. Yeah, and then when they've done that, they'll exchange buffers with someone else. You have to cooperate at some point. Okay? So we're going to do an example of that in a second. But let's imagine, can you see this in the back? You've got this huge array that we need to process. Okay? Now, we're going to basically run a function over this. What I want to do is, I've got an array, which is like on here. We've got a cell inside here. Let's call it x. This is time t0. I'm going to produce a copy of the array. Well, that's a new value of x. Yeah? And I'm going to apply some function to x to produce that. The function here is going to use values x and the ones either side of it, yeah, to produce that new value. And that's going to be the plan. Effectively, what we're going to do in a minute is I'm going to simulate a metal bar. One end of the metal bar is hot, the other end is cold. What's going to happen over time? Energy should go from this end to this end. Right? That's the plan. That's what we're going to simulate. In order to do that, we're going to do this kind of algorithm. So how do we break this data up? There's a couple of obvious things we could do here. We could say that one core, if you've got 4 cores, for example, has that first element to process and the 4th one, or the 5th one, I guess, the 5th one. Then the 10th one, etc., etc. So we interlace them. Or you could just divide it into quarters and say this core gets this quarter, this core gets this quarter. Which one's better? Does it matter? And on the calculation? Well, we can have 2 buffers, right? This is the input. Yeah, that's the output. Okay, so we can always read these in parallel. Yeah. Sorry? Cache locality. So both these algorithms would work, but the problem is the way CPUs work is when you process memory, it pulls it into cache. If one core is updating this part of memory and another core is updating a similar area of memory, not the same location, but very, very close, you invalidate the cache lines, which means they eject each other's memory from cache. And if you then go on to read that data again or do some processing, you have to reload it from main memory. Okay, so we prefer to actually have cores that were acting on memory that was quite far apart from each other. If they're each of them acting very close to each other, there's a potential that you're going to hit the same cache line. Cache line is around 256 bytes generally. Okay? So generally we want to try and separate stuff. Even in this algorithm here, there will be times when they'll get close to each other, but we're going to try and minimize that. Okay? And if we really care about performance, we definitely make sure that we allocate these quarter chunks of memory completely diverse from each other. Right? Okay, that would be the perfect. Okay, so now, like I said, generally with geometric decomposition, what we care about is each task is going to operate on a quarter, in this case, or 6 in this case on here, and then there's these like boundary conditions. Okay, we have to coordinate access to this. You have to decide when is it safe to exchange buffers. What we don't want to do is, I'll read your value while you're in the middle of changing it. That's not a good plan. Okay, so we need to synchronize at some point. But we'd like to think that these tasks are running in parallel, and at some point, when they've done each iteration, they're effectively going to exchange buffers. So like I said, the example we're about to do in a minute is, it's a hot metal bar, hot at one end, cold at the other. We're going to run a simulation, lots of periods of time, and we're going to work out what the state of the bar is at the end of that time period. Okay. So we're going to have an input buffer, which we're going to run, and then we're going to produce an output buffer. The output buffer then for the next iteration of time is going to become the input buffer, and this is going to be the output buffer. Then this is the input buffer, and that's the output. Yeah? You get the pattern. Yeah? Okay, so let's now look at some code. Do that. Okay, so geometry decomposition. Oh crap. You've got to pretend you can see this. You all seen the film Men in Black? I have one of those devices. Okay. Okay. All stay on my pen? Okay, so this is the sequential algorithm. Okay. Okay, so this is the algorithm I was describing to you. We have two buffers, material 2. Yeah. We have a loop. This is a unit of time. And then inside here we have a piece of code that's running over that array, calculating the new value for a given value of x. Yeah? All good? Okay, so if we run the code, this is a sequential bit. I've still got the reference in it. Okay, so sequential version, running number of calls that are being heard at the moment would only be 1. So that produced us a value of 5 seconds. And then I've got a result here. That's just my attempt at a very crude checksum. Once I've finished, I'm adding up every single byte in the array. Okay? Because the thing is, we don't parallelize this now. For my parallel algorithm to be successful, what must be true? Same number will be good, yeah, and quicker. Yeah. Same number and slower, no good. Okay. Really faster, wrong number, no good too, right? Okay? So it's quite constrained. So whenever you parallelize something, the first thing you do is you don't write a parallel algorithm. You generally write a sequential one, because you've got two things to compare your result against. One, you know what the right number is. It's hopefully a simple algorithm. There's no race conditions or anything like that. And two, you want a benchmark in time to beat. Okay? Just warming up every cause isn't good enough. Okay? Okay? You really do need to beat the sequential version. Okay? So you guys are parallel biscuits, I reckon, now, so let's just go and do this. How are we going to do this? This is the sequential version. We're going to rob the code. Okay, we're going to call this the parallel version. Okay, so what we're going to do in here is we want to break this huge material up into a series of sub-ranges. I already have a class that will do this. It's called range. When we define a range class, it starts at 0 and it's going to end at material.width. Okay? How many chunks should I break this thing into? Or how did that happen? Is that a clue? Yeah, so in this case, yeah, each iteration of the loop has exactly the same cost. Therefore, I can basically divide it up into the same number of calls. If there was an iteration of a loop where the iteration would vary based on the data, then effectively we couldn't use this crude algorithm. Okay? But because we know each iteration has the same cost, we can do this. Okay? So, very crudely, what are we going to do? So we've got a range here. We say int n cores. I'm going to say 4. I've got 8, but there's 4 of a hyperthread. So I've got 4 cores. Yeah? Okay. So what we're going to do here is this. We're going to create a list of okay? And then what I'm going to do is something like this. For each range, subrange in what? Range.create subranges. Sorry, I can't remember. So what that's going to do is, if I had a range, if I defined a range from start at 0, end at 20, that's going to give me 4 ranges, create subranges of 4. It's going to return an object of type range, going from 0 to 3, and 1 from 4 to 7, 8 to whatever, I can get the idea. Yeah? It just breaks it up into series of subranges. So inside here, I'm going to do something like this: tasks.add, task.factory.start new. So again, we just modify the original sequential version. Yeah. Okay. Inside here, I'm not going to go from 1. I'm going to go from subrange.start less than equals. Okay, all good? Okay. And then obviously after it's done that, okay, I'm just going to say task.variable. Sorry? Oh, the new anonymous type. That's really clever, isn't it? Okay, so this is the parallel version. Let's go up here. Let's go that this one should be super fast, right? So we'll see this result first. Okay, ready? You run the code? How are we doing for cores? Is it getting warm in the room? Okay, so the parallel version ran and it took 6.635 seconds. So it's slower. It's got the right number. Okay? Okay? All good? Anybody surprised it had the right number? No? I only got the right number on C# 5 compiler because. Sorry? You got a closure. I think Resharp has summed it up really. I don't think no, Resharp is not native for some reason. Where is it? It's parallel version. Prior to C# 5, this will be bad Mojo because we're looking at this closure variable. So we're creating a closure here. Yeah, subrange is defined here. Yeah, as a C# version 5, the compiler takes a copy of subrange inside here, so you get a closure per iteration. If you compile that to C# version 4, you get a very different result. So that's good. But obviously, it's taking longer. Why is it taking longer? We're using more cores. You saw they're all busy. They're busy doing nothing. That's what my wife always says about me. I'm always busy but not doing anything, as she knows. So what's going on?
Did we watch the cores in the serial version?
You don't trust me?
It might be that it's
Okay, so I'm using lots of cores. Yeah, sequential version's running now. Drop right down. Yeah? And it's faster. Yeah? Happy? Okay. Yeah? So the sequential version was quicker but using less cores, right? What's the reason? Well, how many tasks are we creating here? How many tasks are we creating? Are we? No. We're creating 4 tasks per iteration. How many iterations do you think there are? It's a lot. Okay? I think it's somewhere in the region of. So, what's that? We're creating 400,000 tasks. Imagine if they were kettles. Okay? This will be a lot. Okay? So we don't want to do that, do we? How many tasks do we want to create? 4, okay? So we just need to change the way, which way around we've done. We're just creating lots of work ahead of what we need to do, right? So in here, rather than doing, right, creating this loop here, what do we want to do? Okay, we basically want to bring this outside. So I'm going to take that. So we want to create 4 tasks now, where each task will do all its iterations. That's the plan. Okay. And I need to bring that out. Okay. Okay, so we're going to close. That closes that bracket off. Yeah. Then we close off that. And we close that. Okay, what have I done wrong? Subrange is there, that's there, that's there.
That's what the
Sorry? top level for each, but that's after that.
Another one of them.
Oh yeah. Yes. Okay, so how many tasks are we creating now? 4. Awesome. Is it going to be better? Let's see what happens. Power version took 2.1 seconds. We rock. Compared to what's going to be now? 5. This is awesome. What? It's close enough. Are we happy over there? It's close enough, isn't it? Run it again, and we know why. Yes? We need to synchronize. And previously, we were automatically synchronizing because for each iteration of time, we kicked off 4 tasks. And we waited for all 4 tasks to finish, and then the next iteration of time, we kicked off 4 new tasks. Now all the tasks are free running. Okay? They're just running, each one's doing their own iteration, which means they're getting out of step with each other. So we need to synchronize somehow. Okay, the cheapest way of synchronizing here is going to be using something called a barrier. Okay, so a barrier in .NET 4 basically allows us to have a barrier with a count. And your barrier count, you give the barrier to some threads. So if you have a barrier count 4, we give 4 threads to barrier. When each of them hit the barrier, they call signal and wait, which means they wait at the barrier. When the 4th one hits the barrier drops, and they all carry on running together. So you put a barrier at a point in your code where you want to keep everything in lockstep with each other. Okay? So here, real quick, we just quickly drop in a barrier. It's bad, isn't it? Rich isn't here, and that's what he always does. Let's set end calls here so we can. And then we hit down here. Okay? Hopefully now, quicker, and they get the right result. Yeah? We're happy with that? Okay. Right, so that's geometric decomposition. Okay, so the question is really about minimizing the number of tasks that we've got. What time am I supposed to finish? 5:30, is it? Yes, okay. Just checking. Okay, other types of alignment we've got things like pipeline. Okay, so pipeline basically simulates something we have in a car production line. Henry Ford decided that having 20 people all working on a single car at the same time wasn't very efficient. People getting in each other's way. There's contention, that kind of stuff. His answer to that was create a production line. Every person does a little part of that process and then passes it on to someone else. There's only one person working on a given car at the same time, but we've got 50 cars maybe all in the process of being constructed effectively. So that's what we're talking about here, right? Effectively, we want to be able to process some data, but we want to do it in parallel. Like I said, when we start looking at parallel loops, the problem we have is parallel loops will work, but they don't expect things to happen in order. If you care about order, then parallel loops aren't really going to work for you. Pipelines will work for you. Pipelines allow you effectively to put something in at one end, knowing that the message says the pipeline execute concurrently, but the order in which the messages go in will be exactly the same order in which they're processed. Okay? So if you do some kind of signal processing, so you take an input from the digital string of music and you want to put it through some filters and play it out to speaker, clearly you need to output after digital processing in exactly the same order that it comes in. Otherwise the music doesn't sound good, does it? So we have to process in exactly the same way. So, let's go. So TPL data flow is a perfect answer for this. So we've got a simple bit of code here. So here we've got a piece of code here. Where is it? This is a sequential version. It's got 5 stages, right? So we're going to load some data as a block, process it with a Fourier transform, put it through a low-pass filter, do another Fourier transform, and write it out again. Okay? This is inherently sequential. The order the data goes out into the file needs to be exactly the same order in which we process the original source. Okay? So we need to construct a pipeline. TPL data flow basically allows us to do that. So maybe we map that in TPL data flow, go and roll that for a second. And we do call that parallel version. So, we've got 5 stages of the pipeline. There are different types of blocks that we can use in TPL. Okay? Notice here that the first phase here is a for each. Yeah? This is going to produce many things. So the type of block in the pipeline I want in TPL is a transform block, transform many block. That's going to take a file name and it's going to produce me a complex string. Okay, and stage 1. Okay, and some of you noticed earlier today NuGet was offline. If some of you were coding while you were here today, the NuGet went offline, so the fact from us did. So you get all the TPL data flow from NuGet and move that inside Keyimage. So that's going to be my stage 1. Stage 2 is going to be another transform block, and it's going to take a complex number. And finally, stage 5 is going to be an action block. Okay. So each of these blocks is going to do a different part of this processing. Okay? So transform any block, I need to, when I create one of these, I'm going to give it, takes in a file name, I'm just going to run that piece of code here that says no blocks. No blocks. That's going to be the path you pass in. Okay, so that block is going to run that piece of code. Okay. Stage 2 is another transform block, and that's going to take a complex number again. Right? That was the output of that block, yeah? And it's going to produce another complex array. Buffer, and then we're going to use it for you. 15. Okay. Stage 3 is equal to that, but this time it's going to run the low pass filter. And then finally stage 4, new transform block. That's going to go CB. And then finally stage 5 equals new action block. Hopefully CB goes to, right, let's buffer. So just define a series of blocks, and these are linking together. Okay, and all you do now is stage 1 dot link 2, stage 2, stage 2, stage 2, link 2, stage 3, stage 3, link 2, stage 4, stage 5, and stage 4 even, link 2. Stage 1, dot post. Post. And okay. So, this block of code down here, we just basically change each one of these lines of code into a separate block. It's just blocks. We then link each of the blocks together. The block takes an input, does some processing, passes it on. Effectively, what TPL Airflow will say is each block is going to have its own single thread of execution. So by the time we post the first bit in, Once you take loads of block from this, it's going to pass it on that. Stage 2 starts processing. While stage 2 is processing, stage 1 is loading the next block. Once stage 2 is finished processing, you pass it on to stage 3, picking up the next block from stage 1. After we've processed 5 blocks, all the blocks are currently running in parallel with each other. Exactly the same as Henry Ford's production line. Okay? But as far as we're concerned, we're just passing data into the blocks, passing them along. Okay? Yeah? As long as there's no side effects in that logic, this is very easy to parallelize. Okay? Once we've done that, we're just going to say here's stage 1 dot complete, there is no more happening, and then I can say here's stage 5 completion. Okay, and that will wait for everything to finish. Unfortunately, we just only told stage 1 to complete. When stage 1 is complete, we need to tell stage 2 that there will be no more coming in, then stage 3. The easiest way of doing it is just to pass an option to say propagate. So I can say options. Propagate string. Okay, and what I'm going to do now is just pass these link options into here. Link options. Okay? Right, so this is our parallel version. And I wanted to print a different file actually. Up here. So here I'm going to say time it. Parallel? Okay. And I'm going to reduce the size of this array because we're getting short time. Right, okay. So the sequential version will go first. And we'll see how long it takes to process that file sequentially. Oh, God. And it took 6.8 seconds. Okay. The parallel version, that took 5.2. So that's pretty good actually. That's better than I thought. So there's a speed improvement. Are you happy with that? Was it worth us throwing all that calls at it to get that slight speed improvement? It's not bad. I mean, really, did it require you to be an asynchronous guru? I was just taking lines of code that we ran sequentially and I was just wrapping them inside blocks and saying pass on, pass on. It's not hard. It's pretty simple. The nice thing about TPR data flow is what we're doing is we're declaring parallelism. We're using a declarative mechanism. I can actually start saying now, you know what? I want to start throwing some more threads in different parts of this process. Okay. By default, it will use a single thread per block. But I can say, you know what? You can use multiple threads on different blocks. Message order is still preserved, but you can use multiple threads. So here I can say, if I get this right, 2 cores. What was the time it had to be? About 5 point something seconds. That's something else. What was it? Can you remember?
5.2.
It's running. Okay. So 2 cores equals new execution of really depth options. So here I can say max degrees of parallelism equals do. When I create I don't really want 2 threads loading data from disk, that's not a biggie. But when I actually do the Fourier transform, I'm going to let 2 Fourier transforms run at the same time. Low pass filter, 2 cores. And finally this thread. And then the I/O again, I'm just going to run a single thread. Time to be 5.1. Pilot, sorry? Yeah, that would be handy, wouldn't it? I'll put it just there. Okay, sequential version obviously will be the same. Hopefully, power version loads quicker. So 7 seconds for the sequential version. Okay. Declarative parallelism. We proved that the algorithm works as a single chain of things. As long as you message passing, you're only updating the data that's passed to you, you can time it. And you say, well, I think if I put a few more calls here, and a few here, and a few few here, it'll go faster. You don't have to write lines of code to do that. You don't have to radically restructure your album. It's declarative. I think more cores here would be good. I think more cores here would be good. Okay? And hit presto, we get some good results. Is that easy? Because we make it even easier than that. Right, okay, so, so, the other big place for parallelism is loops. Parallelizing loops. Loops generally do lots and lots of iterations, which represent lots and lots of work. Your ability to write lots of lines of code to do mathematics without using the loop and take a significant amount of time to parallelize is pretty low. You generally, as a developer, looking for loops. That's the big place to parallelize. Okay? The decision is, though, you can only parallelize a loop if you don't care about order. Okay? So, regular for loop. You run that. What's it going to see on the screen? Sorry? Oh, jeez. You all need to leave the conference now if anybody said you'd see the number 20. Okay? Okay? Don't read what's on the screen, read the code. Okay, so it's just in 0 to 90. Yeah? No big surprises? Okay? If the reason for running that code was to produce all values between 0 and 19 inclusive, and I didn't care about the order, I can parallelize it. Okay? To parallelize that loop is the cake. So using the regular for loop, I'm going to use the parallel class for 0, 20, I goes 2, and we're done. So what are we doing here? We're calling a method called for. It takes 2 arguments at the beginning, start and end. These have to be either integers or longs. And then we're providing the loop body. We're providing the loop body by using a lambda, a delegate. It's a method call. What we're saying to the runtime, to the parallel for method is, I want to run this delegate 20 times. Yeah? I don't care what calls you want to map them onto. Okay? And they'll all run in whatever order they run. Okay? That's the plan. Okay? If you run the code, what are we going to see now? Nonsense. I don't think it's a nonsense. We're seeing all the numbers, yeah, but not necessarily the right order. Okay? Yeah?
Can you guarantee it finishes the pricing a whole number before it starts with this?
Guarantees what?
Can you guarantee it's actually going to finish pricing a whole number out before it starts with
Yeah, the console has a lock in synchronization. Yeah, so yeah. Otherwise, if you wrote to the console with 2 messages, what you don't want to do is it ended up in some weird language that you don't understand, right? Okay, so yeah, the console locks. Okay, so you've got some synchronization. All happy with that? Is that easy? Could your grandma do that? That's grandma style programming. VB programmers could do this. Right? This is not hard. Okay? So, you guys now have had your induction into the world of parallel loops, so that's good. So we'll just put that away somewhere. Okay? Out of interest, under the covers, what do you think it's doing quickly? It's using tasks under the covers. How many tasks do you think it's creating? Not 20, that'd be like creating 20 kettles. We don't want to do that, do we? We want to create smaller numbers. Create less. You're absolutely depending on the number of CPUs, depending on how much work you've got. There's all sorts of different things that we use. But under the covers, it definitely isn't doing that. So if I can quickly say here, okay, when I run the loop now, it's going to show me the task ID that's processing the value of I. Okay, we're going to run it. Okay, so we can see task 1 did iteration 0, 1, and 3. Task 2 did 4, 5, 7, 9, 11, 13, 15, and 17. Okay, see, it doesn't know how much work to give to a task, right? I mean, the work you give it could do like that, or it could take forever. And clearly it doesn't want to give you a chunk of work, and you go, well, I'm busy working on this. It needs to work out how long the iteration of the loop is going to time take. So it kind of learns and adapts to this stuff. We can see that the same task is being used for multiple iterations. Okay, all good? Yeah, good. Right, swiftly moving on. So what have we got here? So we've got calculate pi. You all can how to calculate pi? We're not calling math.pi, because that's not fun. Okay. Calculating pi, we can use this algorithm if I just change it. Yeah. This is an approximation of pi. So we all use, yeah, back at work? Every day?
Yeah.
Okay, so this is the algorithm. What do we do? What is fundamentally the algorithm? It's a series of summations. 1 plus 2 plus 3 is the same as 3 plus 2 plus 1, which is the same as 2 plus 1 plus 3. Yeah? Do we care about the order of summation? No, as long as it's into mathematics, okay, strictly speaking. Doubles, different kettle of fish. However, for this algorithm, you guys are not uber geeks. You'll be happy with the value of pi being what? 3.14. Oh, here we go, we got one down the throat. How many decimal places do you know pi to?
That's about it.
Oh, really? Oh, okay. Okay, unless you live in America, the state of Illinois, I think it was, or was it Idaho, I can't remember. One day, they decided that pi was too complex for their students. And they decided the state to simplify pi. Now, I say simplify it to 4, but that's probably been a little bit disingenuous, okay? It was 3.14, okay? Because it, it makes the maths easier, doesn't it? Or the math easier, whatever, okay? Obviously, circles didn't look very good. But anyway, they almost passed it as a state law. It's still in the statute books. A mathematician was in the courthouse that day, and he stopped it from happening. Okay, so that's the only reason it didn't happen. It's on Wikipedia, so that's not true. Okay, so you guys are parallel pi parallel loop gurus now. So what am I going to do here? This is going to be parallel pi. So parallel pi, what are we going to change? Get rid of the for loop? Yeah. And put in parallel dot 4. Yeah? Okay? So, we're going to go from what? 3 to pi iterations. Steps of parallel 4 already counts in ones. Okay, well, we're software developers, we can work on that. So we'll change that to 0. Go to pi iterations minus 3. 2 loop index int I equals loop index times 2 plus 3. All good? Close it. Excellent. Is that easy? Basically. So up here now, here we've got calculate pi sequential pi. Okay? Pilot run it, ship it, hopefully. What do you reckon? Good? So sequential pi took just under a second. That wasn't quick enough, right? Let's go run it again. Here he goes. Whoa, lots of cores. Wood's getting warm. It took 2.6 seconds. What do you think the result is? Not even the state of Illinois would be happy with that. So, this is bad. Why is it wrong? There's two things that are wrong with this code, isn't there? One, it's taking too long, and even when it finishes, it's got the wrong result. So what's wrong? Here it is. That multiplier isn't going to work. Why?
Because it relies on being in alternating order and doing that.
Yeah, you see, parallel 4 is just a wrapper over multi-threaded programming. What have we got here? We've got multiple threads running, sharing a variable called pi and multiplier. Okay? Is this going to work out well? Clearly not. Okay? So just because parallel 4 doesn't talk about the word thread or task, doesn't mean that's not what's under the covers. I've shown you that when parallel 4 runs, it creates tasks. This is multi-threaded code. Could we use synchronization primitives? Would that help here? We put lock statements around stuff. Would that help? We might get the right value of pi. What would the performance be like? Even worse. Okay? We've got performance problems here. Okay? Because we're updating the same memory locations. We're getting the wrong result, but we're getting slower performance because of invalidating each other's caches. Okay? So in order to make this work, we really need each task that gets involved in the loop to run independently of each other. So rather than sharing state with another task, they need to have their own local value of pi. When every task is finished executing, Yeah? That each one will say, here's my local value, here's my local value, here's my local value, and another piece of logic adds them all together again. Okay? So that's what we kind of want to do. At this moment, Microsoft demo team are a little bit unhappy because this isn't going to be as pretty now. At the moment, this looks kind of cool. And if this works, life would be great. Okay? Unfortunately, now we're going to do the computer science bit. So what we're going to do now is, this body's going to get a little bit more complicated. So it's going to break up down to something like this. Each time we execute an iteration of the loop, yeah, Power of 4 decides to give it to an existing task, yeah, or create a new task. Yeah? The first time a task gets used for some range of the loop, we have the opportunity to run some code. This code we can run, we can produce a function of t, which means we can return what? Anything we like. Okay? That value that we return is our local value of pi. It's our initialization. And when the task, just before the task gets used, it calls out our method. Whatever we return gets passed to the task. The task can act on it, knowing that it's the only person who's got this. It updates it. When it's done, it returns it. If that same task gets used again for another iteration, it gets given its own value back again. Okay, so it gets its own value go around the loop. Each new task that's introduced, it runs our initialization method, which means it now gets its own local copy of its own local initialization. Okay? All good? Okay, so, real quick. We're going to write a method here. We're providing a method that produces a double. Every time a new task is used, the new task gets given a double of 0. Okay? Now, instead of our body gets taken just a loop index, it gets a loop index, loop state, and a local pi. The first time a task is used for an iteration, it's going to, that value there is going to be that value there. Okay? With then inside here, we're going to use that value. We're not going to update pi, we're going to update local pi. Then when we're done, we're going to return. Okay? We've still got a problem with the multiplier, so let's move that. Yeah. Let's move that into the multiplier just flips from -1 to 1, -1 to 1, -1 to 1. So here we could say simply loop index modulus 2 equals 0. Okay? Alright. So now everything that's happening inside here is local to this. Yeah? There's no shared state. Okay. But obviously we said we need to combine the result. So here we say
We delete the multiplier.
oh yes, thank you very much. Yes, save the performance. Yeah. And then here we'll say local pi goes to, and inside here we'll say pi plus equals. Okay? So let's compile that. Oh, lots of errors. What are we doing on here?
About where you are there, about that one. You need one on the switch number.
That'd be good. I'll see what I've done.
0.0.
Oh, that'd be a plan, yeah, thank you. Why didn't you say that? Okay, let's go run the code. See, you ever wonder pair programming never works? Pair programming never works, does it? Right, let's go run the code. So hopefully now, here's our power wedge. Oh, are we quicker? Excellent. Okay, now me and Rich just have a rule of work. You have to run your code 3 times before you check it. Okay. Is the value of pi the same? It's close enough, okay? But because we do double mathematics and precision, you're never going to get the same. Is it good? Yeah, it's not going to work for me later. Yes! Is this a good value? The state of Illinois is perfect. So, we ran it 3 times, and that final one before we checked the code in, unfortunately it was 4, okay? Bummer. Well, maybe that didn't happen. Maybe it was a solar flare, and it just screwed up all the electrons on the machine. If we run the code again, We're good again. It just didn't happen, right? You've all done that at work, haven't you? So, what's going wrong? What's going on with this? Why is this going on? You see, this piece of code is the combining line. When does that run? The last time a task is used for an iteration, it runs that code. If two tasks finish at the same time, that piece of code is going to run at the same time with two different threads, which means that is not a thread-safe operation. How do we make it thread-safe? We have to use a lot, right? But we're only using that at the point when we combine stuff. We're not using it for every iteration. Yeah, so quickly here, I'm just going to go object, combining lock. And then down here, I'm just going to say here real quick. Oh, combine, run it. I am now. Okay, so let's go run the code. Now, I'm not going to run it through time, but hopefully we'll see. But effectively now, hopefully we should get the same value. Well, ish. Okay. Yeah, all good? Okay? So, like I said, it's really important to definitely write some code that you know what the expected result is. And you need to run your parallel version many times on a range of different hardware platforms if you are going to have some confidence that you're going to produce you the right result.
I guess that's those variables, those are stackable.
So, which one?
Variables you have to stack.
Well, at the moment, the one I'm using is a double, which is a value type. Right? So the value type is just getting returned and it's getting reused again. Obviously, there's nothing stopping that lambda expression creating a new object.
No, I'm thinking because first it was slower, and you just said it was a cache. So I'm guessing by changing to that, the objects are actually more the variables. You're getting actually separating them on the memory or on.
Yeah, these are going to live on the stack at this point, right? So each thread has its own stack space, so they're going to live on the stack because they're value types, right? Yeah. Obviously, if we allocate memory, we might have more issues with that counting. What about the performance then? You happy with that? Really? Really? How many cores? 4. What speed have we got? You'll say lots over there. So, it's not brilliant. Why isn't it brilliant? The lock? No, it's not the lock. Number of iterations? What iterations? I can reduce the number of iterations of pi, yeah, but that's not. But what iterations? Close.
No, what I mean is maybe number of tasks, splitting such a smaller task.
Yeah, okay. So, this is a parallel loop, okay? Well, actually, if we scroll up here, this is a sequential loop. What's this doing? What's the CPU doing? It's incrementing this value I, yeah? Does some maths, and then it does a jump back to here. Yeah? That's quite a quick operation. Okay? So a loop is effectively run some code and then go to back to the top. Do a comparison, go to that's what it is. What does a parallel loop look like?
Create new tasks.
Not doesn't create, well, it creates some tasks, doesn't create a task per iteration. But what it definitely does per iteration is why. Well, what is the body here? It's a delegate, it's a lambda, it's a delegate, which means the compiler turns that into a what? It's not magic. This is a method, right? Which is quicker, a method call or a simple jump instruction? Jump instructions are really quick. You make a method call, that's way expensive. Fine for a delegate, even more expensive. You've got extra cost here above and beyond what we have in the sequential. This is part, we said, the orchestration for parallelism. It costs you extra instructions to make things work in parallel. We're executing a delegate per iteration. How much work are we doing on that delegate per iteration? Very little. So we're paying this huge cost for delegate invocation for a tiny bit of work to do in parallel. What we really want to do is what? Pay that amount of cost for setup and have that amount running in parallel. Okay? So that piece of the body of the loop here is too small to justify the overhead of parallelism. Bomber. How can we solve that?
Hard code for 3, as it were, iterations.
Do you get paid for line code? If you did, that'd be an awesome part, yeah? It's called loop unrolling, really. And compilers can do that, okay? But yeah, I mean, you could do that. I mean, generally what you're looking for parallelism is you're not looking for a single loop, you're looking for nested loops. You parallelize the outer loop, and the inner loop consists of lots of iterations. So rather than manually unrolling it, you put a loop in it. Now the compiler might unroll it in reality, but you basically build a loop instruction set. We haven't got to.
Is the compiler not able to do any kind of sort of inlining here?
Well, no, it's a delegate.
Optimization.
It's a delegate.
But at a low level, it's going on.
No, because the compiler doesn't understand the framework. Yeah, this one, this one. There's nothing really compiler can do here. So, what we're really looking for in parallelism is an outer loop and an inner loop. In this case, we've only got one loop. We're kind of screwed. Well, you can take any single loop and turn it into 2 loops, or as many loops as you like, can't you? This is a product. Right, a loop that goes from 0 to 5,000 is the same number of iterations as an outer loop that goes from 0 to 100, with an inner loop that goes to 0 to 50. Yeah? Well, the maths right? Yeah? Okay? So we can basically create an outer loop. Okay? So, oof, this is going to be close. Right, so let's go and rewrite this. I'll do this really quick. So not only do we have parallel.for, we have a parallel.for each. Okay. And let's be brave here. Okay, so I'm going to go and do this. Remember the range class that we saw previously? Range, new range. I'm going to say start equals 3, end equals pi iterations. End cause equals 4. And I'm going to do a parallel for each. Okay? So this is like a parallel 4, except it's working on a line. Okay? Range dot create. Give me create subrranges. Okay. Again, we have our initialization. Yeah. I need the comment, don't I? Or just shout at me. Loop range. Loop state. And then inside here, we're going to change that to local. But this time, this is going to go from 3 to go to loop range dot start. And we're just going to multiply that inside. And again, once we've finished our iterations here, we say return local. Yeah, I did the lock again. But I think I've screwed something up. So, okay, and then we obviously need a lock. I won't go away. Okay, so now what have we done? We've this time now basically created an outer loop and now we're going to loop. Yeah? When we invoke the delegate in a parallel way, then for each delegate invocation we're now doing a chunk of work. Okay? Making it worthwhile. Yeah, I get you. Making it worthwhile to execute the question.
What happens if the loop range is split on an even number?
Yeah, well that's just a demo. Yeah, you have to handle that, okay? I'm just trying to, we're trying to produce an example that's relatively simple at the same time trying to show you complexity. But you're absolutely right, you would have to do it. Okay, right, so hopefully now, we're going to do capital pi. Did I call it parallel 4? I don't know why. Okay, let's go run it. Now we're down to 4 in 18 more seconds. Okay? So parallelism can be relatively easy, okay? But depending what kind of results you want, depends on how much effort you put into it. Right? So we already had a speed improvement with the first one. Actually, we put a bit more effort in and we understood what's going on under the covers. We got even better performance further on. Yeah? All happy with that? Yeah? All good? Okay. So what do you think? Is it free lunch? No? Oh shit. Okay. So probably the big place where one of the wings is, which what these F-sharp dudes are hanging out in, is functional programming. This is very similar to pipelines, the TPL data flow. You know, where effectively, as long as we produce an input, it takes it and produces an output. Life is good. Okay? As long as we don't have any side effects, we can effectively run multiple functions in parallel, processing bits data from one another. It does rely on the fact that we okay? In C#, one of the classic places of functional programming is link. Who likes link? What do you love about link? Well, let me first of all, it is called link. If anybody here from Germany, I hate to say this to you, it's not called link Q. Okay? Lots of people from Germany seem to think it's called link Q. It's not, it's link. Okay, let's move on. So we then have this thing called link. Okay? And link, the thing about beautiful about link is it's readable. That's what we love about link. Okay? It's a nice, readable way of expression. The thing about link is, the thing that makes it readable is what? Why is it readable? It's declarative. But it's quite a high-level form of abstraction, isn't it? It hides the mechanics of what's happening under the covers. You know, in effect, from these rows, where, order by, select. These are high-level building blocks. We can just glance at it and understand what's going on. You could unpick it and write it in C#, and you could probably understand it if you looked at every single line, but it's a very high level. Because it's at a very high level, it's a good candidate for parallelism. It's functional programming. You just call the where method, it takes an input, produces an output. Okay? Yeah, because it matches the condition. But it's, because if you understand what where does, you can write a version of parallel where. Select, you know what select does? It takes something and produces something. Yeah? We can write a parallel version of that. There are all these different methods that fundamentally have high-level meaning. And because we compose lots of logic with high-level meanings, we can have parallel versions of these high-level meanings. And because it's functional programming, it means it's relatively easy to parallelize. So we have this thing called p-link. Okay? So let's go and have a quick. We haven't got long, so I can jump to it. Let's go here. Let's go back to pipelines. Okay, this is a version of that pipeline reading link. Okay? Yeah. Load blocks returns an enumerable of complex buffer. Apply the Fourier transform to it to produce another version of the complex buffer now with the Fourier transform. Pass it through a low pass filter, and then do a Fourier transform on it, and then effectively process the result. Okay. Is this easy to understand? Okay. So, we can go and copy that code. And we can change it to the p-link version. Okay? And then all we need to do to make this work faster is just say I know you think I'm smoking stuff. I mean, this is definitely a VB Duke can do this. Right? It is random programming at its extreme. The benefit, this works. I mean, maybe I'm just, guessing here. But if this works, is that easy to read? Is that free lunch? Yeah, you just drop that on, and it's just hopefully magically work. The person reading the code still understand it. Okay? That's the plan. Okay? So, that's compiled. When it compiles, let's go inside the code. So we've got a couple of versions there. We've got a sequential version and we've got a parallel version. I'm going to comment both those now. And I'm just going to change it to define it. And we do the link version. Okay, and let's go to the next. Okay. I want to do one change here. Can you take this together? So just for you guys, I'm going to write the data out, okay, and what we're going to do is we're going to make sure that the parallel version is exactly the same as the sequential. Okay, all good? Okay, sequential version, off it goes, trundling away. It took 6.8 seconds. The peeling version took 2 oh. They looks like different lengths, actually. They are different. You see, this whole algorithm that I created, this pipeline, what did I say the benefit of TPL was? With the blocks. Guarantees order. What do you think peeling does? Doesn't guarantee order. Okay? So it doesn't look great. We can fix it. I don't know why it's giving me different lengths. That's the scary thing. Expensive different lengths.
You change the file name reference.
I don't think I changed the file name. No, because I copied the code, right? I did copy paste. And the only thing I changed was the Apple file name. So it's still not that. But what you can say here is as ordered. Okay. Now that would mean buffering. Yeah, it would mean use extra memory. Okay. But effectively telling peeling, I want you to make sure you spit stuff out in the same order that we process. Okay. So that original buffer that comes in, whatever processing happens to that, that'll be the first thing that comes out from this for each statement here. Yeah? Okay. So hopefully then, I lost them at the conference. Oh, shit. I'm not sure why. I don't see why. I'm using the same file. Input file name. I'm using the same file.
Not some trivial like a new line character.
I'm not sure. Okay, sorry guys, I don't know why. I have to. You get the idea.
Comparing the link output with the peeling output.
Yeah, that's the idea of it. That's it. Let's put it back. Come on. Where's which one I need? Yeah, absolutely. This is not if this doesn't work, I'll fix it. I'll give you a I don't know. It's always worked up to now.
What if you want to both serial?
Whoa. See different names here, isn't it? While it's running, peeling version is writing into peeling amplify, that's right, yeah. And the link version is writing out into link. kind of spooky. Isn't it?
Is there any other referencing that far there?
I don't think so. It's not twice the size, though. Guys, I don't know. Let's move on. I'm sure you're working out.
If you look at the first half of one of the longer farm, does it match the first half?
It's not binary. I don't know if yeah, it's a good idea, but we'll have to have a look. I'm not sure exactly. It works on my machine. Sorry, it's not good definition. Anyway, so there's a couple of things quickly, just very quickly about peeling. It should have looked awesome. Okay. The thing about peeling is it works on iNumerable, it works best on arrays and lists. Trying to use an iNumerable doesn't know how much data there is, it's hard for it to partition. So if you aren't doing performance with it, really work on arrays and lists, don't just purely by iNumerable. But the good news is, it should be a free lunch, just has power and should give you room. Finally, real quick, traveling salesman problem. This problem is, salesman wants to visit how many cities? Loads, 10, 15, whatever. You've got to work out the shortest route. How many combinations are there? Lots, yes. Here's a fact. So it's a factorial problem. So 15 cities produce a hell of a lot of combinations, right? You try and do that through brute force. It took me on 8 calls, 18 days. That's a hell of a lot, right? Okay. Monte Carlo, however, is a different way of solving. You can't work out every combination in a time frame that's reasonable. You have to make a guess. That's what you do as a human, right? So the computer basically take guesses, right? So I can run a simulation that just basically says you've got 2 seconds to find me the route. And it can play some guesses. And if I run Monte Carlo on a single call with 2 seconds, just making guesses, I know the perfect route, because I waited 18 days to find out. I can then basically run Monte Carlo against it and say, well, how good is Monte Carlo? Well, when I ran a single call in 2 seconds, I was getting anywhere between 0, it was always, sometimes it got the perfect answer, and other times it was 45% out. That's a hell of a guess, right? That's a bit of a bit back. However, all we're doing is having a single call, just making random guesses. If we then have 8 calls doing exactly the same thing in parallel, the chances now of getting the right number gets massively increased. In fact, when I ran it again over 100 iterations, the results were somewhere between less than 4% out and perfect answer. Okay? Zero. No, I'll get perfect. Well, but it will happen, normal iteration. Oh, we're running the same. Yeah, so effectively this is the kind of graph here. As you add more and more cores, getting closer and closer always down to the end of the result. Okay? Lots of people with banks, lots of places where you can't know the actual answer uses Monte Carlo. You can actually use Monte Carlo to find the value of pi. Do you know that? Draw a square, inside the square draw a circle. Take $1,000, which have those lying around, and you throw them randomly at the dart pools. Some will land in the circle, some will land hopefully inside the square somewhere, right? Okay, that's the plan. Yeah. What should the ratio between the two be? What's the area of a square? Yeah, r squared. Well, you do 2. No, it'll be 4r squared, right? Yeah, is that right? 2r squared. Right? What's the value of the area of the circle? Pi r squared. You basically work out the relationship between the two. Add up the ratio between the darts in the square bit and darts in the circle, and you get the value of pi. Write the code to do that. Unfortunately, to write the code to do that, I have to know pi first to draw the circle. But very quickly, then Monte Carlo, real quickly, we'll finish it. Monte Carlo. Here's Monte Carlo. Okay, so hopefully now, average benchmark, number of calls. I'm going to change this to 1 call. It's going to make a guess on that same trick. The first attempt was 36% out. That sucks. 28%. 35%. 6%. 6 again. 4. Okay. 8, 9, 10. The average is 12% out. So your salesman on average will go 12% longer than he needed to. Okay. I'm still going to do it in 2 seconds, but instead I'm going to use 8 calls. 8 people making random guesses. And after 2 seconds, you take the best guess from one of those 8, and that's the value you take forward. And again, 0.5% ham, 0.3% ham, 0.9% ham, 1.4, 1.7, perfect, see? Doubting touch. You know what? 0.88, that's probably good enough. Okay? Yeah? So sometimes you don't need the absolute perfect value, you need a value that's good enough in a meaningful time frame. Okay? Monte Carlo gives you that. Okay, right, nothing. Okay, lots of ways to parallelize. We looked at lots of different ways for simple fork and join, divide and conquer. Pipelines using TPL. Pipelines using peeling. Peeling is definitely one of the best places for ease of parallelism, as long as you don't have any side effects. Be careful though, link is not performance technology. Peeling will go faster than link lots of times, but that doesn't mean you couldn't write it faster some other way. But the nice thing is, anybody can almost parallelize a piece of link. Right? But the most important thing you have to remember is before you parallelize, you have to benchmark. Peeling's perfect, right? You know what? The same code, just put as parallel at the end, benchmark it. If it's faster, you get the same result, life is good. Other more sophisticated stuff like Monte Carlo, we don't necessarily want the perfect answer, we just need an answer in a meaningful time frame. Multiple cores will basically take lots of guesses and will take the best guess. It's not a complete random guess, there's lots of algorithms you can use for working out how best to make the next guess. And there's lots of skills. But effectively, lots of ways to parallelize. Is there free lunch back? Maybe with peeling. Well, not today. Okay, that's everything. If you want to know more about stuff, we have a lovely book, okay, that effectively describes all this kind of stuff inside the book. If you've got any questions, please feel free to email me. If you want the code will go up with the working version of peeling. We'll go up to that website. Other than that, one more thing. I usually throw out a book. Is he gone? The dude's gone. He asked me, could he buy the book in London? And he's been out on the flight, but he's left the room. So here's a book. Oh, shit, all the hands have gone up already, haven't they? Rich isn't here to tell me off. I don't know. I'll spin round a bit.